Okay, parameter learning. This is the lesser problem. I mean, there's a whole huge literature on it as well. So just probably in terms of weight of publication, it's not the lesser problem. Problems with data, well, you get noise, you get missing values, you get small samples, and hopefully you can overcome those things. Another source for parameters are the experts themselves, but as I said, you get biases, you get miscalibration. Does anyone know what miscalibration in this context is? This hasn't been discussed, right? Or wrong?
I briefly touched on it in the Delphi session.
Okay. Does anyone know what it means?
Communication gaps?
Nope. Miscalibrated experts. Doesn't bring to mind anything. Okay.
They're not the expert in what this.
No,
what
they're
being asked.
No. Miscalibration is almost a universal human phenomenon. Basically, it means if you're estimating the probability of some outcome, then you're either underestimating or overestimating that probability. So correct calibration means if you say that there's a 70% chance of rain tomorrow, then 7 out of 10 times you say that, there is rain tomorrow. And if it's 9 out of 10 times or 6 out of 10 times, then you're miscalibrated. So ideally, you eliminate miscalibration. Human bias, of course, will introduce a kind of miscalibration. One of the human biases that's quite common is overconfidence. We all love ourselves and our own opinions. I know everything about the world, I'm pretty sure. And so when I say it's a 90% chance, by God, it's a 90% chance. Do you agree with me? Well, anyway, most people think that way, not consciously, but subconsciously, and so they're overconfident. So if they think their team is really likely to win, right, they won't say 80% to 20% chance. They'll say it's 99 times out of 100. Or what was that movie about the killing of Osama bin Laden? What's the name of that movie? I've forgotten. Anyway, Catherine Bigelow directed it, and I forget what the hell she called the movie. But in it, there was a meeting where the chief CIA protagonist of Osama bin Laden being in this one house, right? They were asking about the probability. Should we move in? What's the probability? And she said, oh, it's 95%. And if you guys weren't here, I'd just say 100%. God damn it. So that's overconfidence, right? It's almost universal. Who is not overconfident? Well, until recently, I would have said it's just weather forecasters who tend to be well calibrated because they get huge amounts of feedback. But recently we heard that intelligence analysts are underconfident because they've been beaten over the head over and over again about how people are overconfident, so they have the opposite problem now. So it's possible to get rid of your miscalibration and adopt another one. These are just some of the cognitive biases. People are prone to huge numbers of biases. Availability is one. Sorry. Oh, sorry. No, I take that back. This is referring to how you get experts. You might not be able to get them. That's what that means. Availability is also a cognitive bias, but well, we won't go there. Solutions. You can test for bias in all kinds of ways, including against data, but also you can give people tests and just see if they're biased when you know what the probabilities of things are and you ask them and they're supposed to know and whatever. So like personality inventories, they frequently put in little subtests to see if you're lying, if you're cheating, if you're prone to cheating. So you can do things like that. Combined with data, okay, so there's all kinds of stuff you can do. Other parameter sources, there's literature. As I mentioned, if you don't have an expert, you don't have data, then if somebody has done prior studies, you can have a look at those things. Problems with them, well, frequently the parameters are actually, like in the IARPA problem descriptions, they're kind of vague. They don't exactly say, for these parents, right, and this child, this is the CPT. They're not going to say that. They're going to say things like, there's a strong dependency between this and that and a weak one here, and sometimes they'll give you numbers and sometimes they won't. So that's a problem. There's a bias inherent in publication. Somebody must have gotten a result, otherwise their publication was rejected. So that means all the real non-results, right, are not published. You have to guess about them. There are some attempts, recent attempts to respond to that bias, but they're kind of limited. We'll see where that goes in the future, I suppose. Combining different sources can be problematic. This p-hacking actually refers to not really combining different sources, but going after multiple examples until you find one that tells the story you want. That's a kind of confirmation bias. Combining different sources is typically done via meta-analysis, which isn't p-hacking and can be legitimate. Okay, learning parameters. The basic concept is just you have some joint sample and you have, let's say, a couple of parents and a child, and you're trying to learn what's the probability of the child taking a certain state given the parents are in some other states. So the really simple-minded approach that is employed in a lot of the software is just counting. So you just go through the sample, find all the cases that match the parents' values that are of interest for this particular parameter, and then you see what the child value is in that particular case, and just count all of the ones where the child is positive or negative or whatever, and there you go, you have your estimate. So that's Spiegelhalter-Lauritsen algorithm does that already in 1990. This is assuming parameter independence, which really is actually a fairly big deal. So what that means is that in the CPT, it's trying to trip me. Here, I'll give you a really trivial example, a silly example. Let's say you're trying to decide whether to take your umbrella with you or not. Okay, so there's either rain or no rain. So usually taking your umbrella doesn't have any effect on rainfall, right? We assume so. Okay, so let's say the probability of rain is 0.2, and if you don't take the umbrella, it's still 0.2. This is parameter dependence. Parameter independence means you assume that there's no relationship between these numbers. They could be the same, but they could be anything. Okay, well, if you know the way the world works, you know there's a dependency, which is equality. And you can use that dependency to simplify the number of the estimation problem. You reduce by 1 the number of parameters you have to estimate for this, and whatever, that's the same parameter. Okay, well, if you know that there's a dependency, then you can take advantage of that. Or if you suspect that there's a dependency, you can take advantage of that. For example, you can, instead of learning a full CPT, you can learn a decision tree, which tells you that when you have the umbrella, you have a certain probability of rain, and so on. So anyway, with decision trees, these would just be automatically combined. So that was the hybrid learning that I skipped over earlier. In hybrid learning, in CAML, you can either learn a CPT, or you can learn a decision tree relating the parents with the children, or you can do other things. There's one other thing you can do in CAML, which is learn a logit model, which is yet another alternative that combines parameters effectively. Okay, so if you don't assume parameter independence, and in fact there is a dependence, then you can do a better job. Why is it better? Well, you have fewer parameters to estimate effectively. You're using more data per parameter. You can estimate it that much more accurately or quickly. Spiegelhalter-Lauritsen, as I was saying, is just a count. It's effectively doing what I said, filtering through the data, finding matching cases, counting things up, and estimating directly from the count. Everything is treated as independent. And another drawback is that if you have a lot of parameters, if the CPT is large that you're trying to estimate, and your data isn't enormous, then you're probably going to end up with some parameters which have no cases. So the count is 0. And CPTs and Bayesian nets don't like the number 0. They're kind of allergic to them. Things go crazy when you have a 0 there. So you have to avoid that. Netica, for example, just sticks a 1 in every cell before you start counting. So it has a uniform prior on everything, and the data dominate because if there's like 1,000 sample size or something, then not too many things are going to remain 1. So that's a nice simple-minded approach to, okay. All right, there's some example, it doesn't matter. Okay, so there's basic counting. There's expectation maximization, gradient descent, and other techniques also for learning parameters, which can be more effective than counting, especially when there's stuff like missing data, when some of the observations are gone missing. EM and gradient descent can cope with that. And are we doing another demo?
We don't have to. This one's optional.
Do you want to do a demo? I can't do this. I don't even know what it is.
Steroid. For learning to begin.
It's about football team and
Football team and steroid use?
We can demo it rather than do an exercise.
Yeah.
Because,
I guess that's what demo means, not an exercise, but I don't know the demo, so.
It could be a demo or an exercise.
Ah.
So I think about time both. I think a demo is pretty.
I'm totally unfamiliar with either, so I won't be doing this. I'll just watch you do it.
The learn parameters thing there. So
You want to skip this, in other words? All right, that's fine. Doesn't bother me. Anyway, presumably it was a demo of parameter learning. But you can play with Genie. You already know now how to play with Genie, so you can learn parameters. You can generate parameters from any Bayesian net, so you could load it up in Genie, generate a bunch of data, a joint sample. You could introduce noise in the way of missing data by just going in and zapping your data file, and then run EM or gradient descent or whatever and see how it does. Okay, yeah, this is just describing a little bit more what EM and gradient descent are. Basically, they're stochastic methods. This is an iterative method where you estimate some of your parameters, are presumably unknown, right? So you estimate them, and then you generate some data corresponding to the missing values. You don't mess with the non-missing values, but you generate, that's what estimating missing data means. And then from this new data set, you re-estimate your parameters. You keep on cycling through this, and you typically converge. You might well converge on a local minimum, which gives you a bad parameter set, but at least you'll converge. And if you don't like the parameters, you can always kick them and start again.